this video, we'll be talking about transformations of functions. Before we dive into what a transformation is, let's talk about tattoos. If you didn't know this about me, I have a couple of tattoos and I'd like to get several more. I just don't know exactly what I would want to get tattoos of. Why are we talking about tattoos and what do they have to do with functions? Well, suppose I want to get this bird tattoo somewhere on my back, and this is the picture that is in the photo book at the tattoo parlor. What can I do to edit this picture so that it doesn't necessarily look exactly this way on my body? Well, one thing that I can do is I can move it around. So maybe I want it on my upper back, so I can move it up, or I could move it down. This is known as a shift. And more specifically, it's called a vertical shift because I'm moving it up or moving it down. We could also do something called a horizontal shift where I move it to the right or I move it to the left. That is called a horizontal shift. Now, we could also do a vertical stretch, which is, let's say I think that this should be slightly taller, then I can stretch it vertically this way. That is called a vertical stretch, or I can shrink it vertically and do it like that. I can also do a horizontal shrink or compression by doing it like that. I can also do a horizontal stretch by doing it like that. That doesn't look proportional, so I'm going to try to return it this way, and maybe this is the size of the tattoo that I want. What else can I do from here? You might say we could do a rotation, but specifically in this section, we're not going to deal with rotation so much as what are called reflections. Let's say I wanted this tattoo to be upside down. This is called a reflection. I could reflect it so that it's upside down. I'm going to change it back. I could also reflect it or mirror it so that the bird is looking in the opposite direction. So this is a different type of reflection. I can reflect it that way. And typically we call that a reflection over the vertical axis or a reflection over the y-axis. I'm going to go ahead and switch it back. And then again, one more time, this is called a reflection over the horizontal axis or a reflection over the x-axis. So let's tie this in with functions. Let's define a shift. If c is some positive number, to graph y equals f of x plus c, you take the graph of y equals f of x and you shift it upwards c units. So for example, really quickly, let's say I had the function y, or let's call it f. So f of x equals x squared. And if I wanted to shift this up, I could change it to y equals x squared plus 3. And so if I did that, we would take all the points on our graph and we would shift it upwards 3 units, and it would look something like that. So that is a shift upwards. Similarly, if we subtracted some positive number c on the outside of our function, that would mean we would shift downwards. These two are called vertical shifts. And then if we add or subtract c on the inside of our function, meaning that the plus or minus c is inside our parentheses, that is going to move it left or right. And these are called horizontal shifts. So up next, we have stretches. We saw this with the tattoo. We have vertical stretching or shrinking and horizontal stretching or shrinking. I will let you read over those. And then we also have reflections or mirroring. So if we want to reflect over the y-axis, we evaluate f of negative x, or in other words, we multiply the input by -1. And if we want to reflect over the x-axis, then we multiply the outside of the function by -1, and that will cause it to reflect. For example, we know that y equals x squared looks something like this, and if I multiply that by -1, we get y equals -x squared. That will mirror it or reflect it over the x-axis. And so that's what happens when we multiply it the outside of the function by -1. And here, lastly, we can talk about symmetry, which is not necessarily a type of transformation, but still comes into play. So an even function is one that if f of -x is equal to f of x for every value of x in the domain of f, then f is called an even function and its graph is symmetric by reflection over the y-axis. So an example of that would be the function f of x equals x squared, because if I were to plug in f of -x and evaluate that, that would be the quantity -x squared, which if you multiply -x times -x, that gives you x squared, and this is equal to f of x, and which is the original function. So, and we can also tell that it's even from the graph, because if I graphed y equals x squared, if I reflected that over the y-axis, that would just return the exact same image. Now, if f of -x is equal to negative f of x for every value of x in the domain of f, then f is called an odd function, and its graph is symmetric over the origin. This is another way of saying that if you rotate the graph, rotation by 180 degrees results in the same graph. So that's another way to say that something is symmetric about the or over the origin. Example 1 says, for each of the graphs, describe the transformation of f of x, which is graphed in blue, into the new function, red, in words, and write a formula for the new functions in terms of f of x. Now, really quickly, again, the original function f of x is graphed in blue, and sometimes you'll hear the original function called the parent function or the parent graph. And then the new transformed function or graph will sometimes be called the child graph or the child function. So that's just some nomenclature. So in part A, we have an upward facing parabola, and to get the graph of the red function, what we do is we reflect over the x-axis. And if we wanted to come up with a formula for the red graph, because we are reflecting over the x-axis, this would have a formula of negative f of x. And we want the negative on the outside. And if you forgot, feel free to go back to the previous page where we see that if we reflect over the x-axis, then we multiply the outside by -1. Okay, so let's look at part B. One thing you'll notice is that this kind of looks like a check mark, and then to get to the red graph, we have to mirror that. So what I'm going to do is I'm going to take this graph and I'm going to mirror it about the y-axis. So I'm just going to go ahead and draw it with a dotted or dashed line. So that tells us that we have a reflection over the y-axis. And then it looks like we have some shifts that are happening. And what I'm going to do is I'm going to follow this bottom point right here. So what's happening is it's moving left 1 unit, and then it's moving down 4 units, and then it's ending there. And so are all the other points as well. So the next step we could say is that we shift left 1 unit, and then we shift down 4 units. And I want to capture all of these in a formula. So if we're talking about the reflection, we throw in a negative side on the inside. And then I want an extra set of parentheses. And then we have x, and we're shifting left 1 unit, which means on the inside of this inner set of parentheses, I want an x plus 1, and then I'm going to close that parenthesis, and then I need to close the next set of parentheses as well, and then we're shifting down 4 units, so on my outside of any of those parentheses, I would include a -4, and that is our final answer for part B. Now, for part C, I'm going to follow the blue graph we have this x-intercept here, and what's happening is that's getting shifted 1, 2 units to the left, and then 1 unit up. And notice that that's happening for the other points as well. For example, if I followed this little valley here, this would be going left 1, 2, and then going up 1 unit. So we can see that we have a shift left 2 units, and then we have a shift up 1 unit. And if I wanted to capture that in a formula, what we would do is on the inside of our parentheses, so we would have f of x plus 2. That is what gives us a shift to the left 2 units. And then if we're shifting up 1 unit, I want to add a plus 1 on the outside of our parentheses. And that's the formula there. Okay, so let's look at part D. We have a wider graph as a parent function starting off with the blue, and I'm going to kind of make note of where this point ends up and where this point ends up. So this bottom ordered pair is located at 2, -2. And then what's happening is it's getting smushed in, and now that new ordered pair is 1, -2. And then here, this is at 4, 1, and that's getting smushed into that ordered pair, which that ordered pair has the location 2, 1. So what's happening is that the x-coordinates are getting cut in half. So another way that we can say that is that the graph has a horizontal shrink or a horizontal compression. So horizontally compress or shrink by a factor of 1/2. So how do we edit the graph? Or excuse me, how do we edit the formula for f of x? If you go back and look, the way that we do that is we multiply the inside by a 2. So f of 2x would give us a transformed graph so that it is horizontally compressed by a factor of 1/2. That concludes this example. Example 2 says determine if the graphs of the functions below are even, odd, or neither. So let's look at graph A. I have a line that goes through the origin, and if I were to reflect this, or excuse me, if I were to take these ordered pairs and I rotated them in either direction 180 degrees, notice that they would rotate into those same spots, and essentially I'd have the exact same graph. So this is an example of an odd function. In part B, if I were to mirror this or reflect this graph over the y-axis, it would give me the exact same graph, which means that this is an example of an even function. And in part C, if I took this graph and rotated it about the origin, or reflected it about the origin, or rotated it 180 degrees, we'd get the exact same graph. So this is odd. Example 3 says determine if the following functions are even, odd, or neither. In this scenario, we're not given the graphs of these functions, and we may not know what the graphs look like. So we're going to use the algebraic definition. For part A, I want to evaluate g of -s and see what that gives us. So let's go ahead and plug in -s anywhere we see an s. Okay, so both of our exponents are even, and when you raise a negative value to an even power, what happens is the negative sign disappears. So this is equivalent to 4s to the 8th power minus 5s squared plus 1. And if you'll notice, this is the exact same function that we started with. So what we've ultimately been able to show is that g of -s is equal to g of s. So what that means is if we were to plug in a negative value, say -4 or +4, they would both provide the same output value. This means that the graph is symmetric about the y-axis, and this tells us that we have an even function. Let's do something similar for part B. I'm going to go ahead and evaluate f of negative x, and anywhere I see an x, I'm going to replace it with a negative x. Now, both of these powers are odd, so what's going to happen is negative x times negative x times negative x is negative x cubed, and then 8 times negative x is minus 8x. Now something you might notice is that both of these terms are negative, so I can factor out a negative sign, and that would leave me with x cubed plus 8x on the inside of my parentheses. Now, an observation that you might make is that the thing inside of the parentheses is the same as the function that we started with. So this is equal to negative f of x, or f of x times negative 1, because we have that f of negative x is equal to negative f of x. From the definition, we can conclude that this is an odd function. So let's talk about the order in which we perform transformations. When you have a function f of x and are looking at the transformation, this is important because it should look like a times f times b times x plus c. Oh, excuse me. This should be a times f of b times x plus c and then plus d. You want to make sure to do the reflections before shifts when going through the various transformations. So in certain instances, the order in which you do the transformations does not matter. For example, if I had a dot here and this represented my function, it's just a single ordered pair, which can represent a function. So let's say this is the ordered pair 0, 0, and I wanted to perform two different shifts. So let's say I shifted up 4 units and then right 3 units. That would still, so here's 3 units. That would end me up here at the ordered pair 3, 4. If I did that in an alternate order though, if I went right 3 units and then up 4 units, that would still end me at the same graph. However, if we have a combination of shifts and reflections, then the order does matter, and you have to do the reflections before the shifts. Example 4 says, describe each of the following transformations of f of x in words. Be cautious of the order in which you write your transformations. So in part A, we have f of x minus 2, and because it's on the inside of the parentheses, what we would do is we would shift right 2 units. So that's the answer for part A. For part B, I have a minus 3 outside of the parentheses, so that would be a shift down 3 units. Part C, we have two different transformations. We have the minus 1 on the inside of the parentheses. That's going to be a shift right 1 unit. And then the plus 10 on the outside of the parentheses is going to be a shift up 10 units. Okay, for part D, we have f of negative x plus 5. So remember, we need to do reflections before shifts, so the order matters on this one. I'm going to reflect over the y-axis. And then I'm going to shift up 5 units. Oh, my apologies. This was a vertical shift. So in this particular case, we would have gotten the same graph even if we swapped the order of these. So in this particular case, we would still get the same answer or the same graph, but let's just practice good habits. So we have a reflection and we'll do that before our shift. So that's the answer for part D. Let's go ahead and maybe move on to a different one. Let's work on I. So I, we have several different transformations that are taking place. And again, we want to make sure that we do reflections before our shifts. So let's deal with the 1/2 first. What that's going to do is it's going to stretch horizontally by a factor of 2. Then we can deal with the reflection on the outside. So we would reflect over the x-axis. And then the next one we can shift left 1 unit. And then the last thing is we would shift down 3 units. Now let's go over the answer for part L, and we want to do reflections before shifts, but we could start off with the vertical stretch. So vertically stretch by a factor of 4. So that's because the outside of the function is being multiplied by 4. And then we can now deal with the negatives. So reflect over the x-axis. Then we can reflect over the y-axis. Since we have 2 different negatives that are being multiplied, we have the negative on the outside and we also have the negative on the inside. And now we can deal with the shifts. So I have the x plus 3 and then I have the plus 1 on the outside. So we'll shift left 3 units, and then we'll shift up 1 unit. All right, my handwriting was getting a little messy, so I've gone ahead and I've typed out the answers in this peach-colored box. So go ahead and use those to check your answers for this example. Example 5 says match each function with its graph. So in equation 1, we have y equals x squared. This is our parent graph because it has no transformations that are happening to it, and we know that the vertex of this goes through the origin, and because our leading coefficient is positive, it's an upward facing parabola, and the only parabola in our set of graphs that has its vertex at the origin is graph G. So the answer to number 1 is G. For number 2, we have y equals x minus 4 quantity squared plus 2. Really quickly, I'm going to emphasize that our xy plane is split up into 4 quadrants. Here in the upper right corner, we have quadrant 1. Here we have quadrant 2. In the bottom left corner, we have quadrant 3. And in the bottom right corner, we have quadrant 4. So what these is telling us is we are shifting twice, and the shifts that are happening is that we are shifting to the right 4 units and we're shifting up 2 units. And so that means that our vertex is going to be in quadrant 1, and the only graph that has its vertex in quadrant 1 is graph H. For equation 3, now we kind of have the reverse. We're shifting left 4 units and down 2 units, and that would correspond with graph B. In equation number 4, we have y equals negative 2 times x minus 2 squared. So the 2 on the outside is going to have a vertical stretch by a factor of 2. Then the negative on the outside means we have a reflection over the x-axis. And so if you look at all the potential graphs, it has to be a frowny face or a downward facing parabola since our leading coefficient's negative. And there's no vertical shift, so really the only possible options are C and D. And if you're having trouble figuring out which one it is, think about what value makes x minus 2 0. So if I plugged in 2 for x, that would make 2 minus 2 0. 0 squared is 0. So what that tells us is that the vertex of this particular parabola is located at 2, 0, meaning that there is a shift right 2 units. So the only graph that corresponds with that is graph C. Excuse me, I meant to put graph D, not C. D as in delta. Okay, moving on to number 5, we have almost the exact same situation. We're coming back and we can say what value of x makes that 0, and that's negative 2. So that means that the vertex of this graph is at negative 2, 0, which is right here. So that's got to be the one that is graph C, as in Charlie. Then looking at the next one, we have reflection over the x-axis and a vertical compression by a factor of 1/2 and a shift down 4 units. All of that is describing graph A. And then we only have 2 graphs left. And so for 7, that's going to give us graph F. And then for 8, that is going to be graph E. Oh, look, it spells the word cafe. Example 6 says there are 2 functions graphed below, f of x and g of x. As you can see, f of x is graphed on the left and g of x is graphed on the right. Part A says identify the domain and range of f and g. So let's start with the graph on the left, and we want to identify its domain and range. Remember that the domain is all of the possible input values, or in this case, all the possible x values. So look at the graph, it's a continuous function because I don't need to pick up my pen or pencil in order to graph it in its entirety, and there's no breaks in it. So here, the leftmost x value is -1, and then it goes all the way to +2. So for this graph, our domain is bracket -1 to +2. And then our range, now we want to look at the y values. So the lowest y value happens at 0, and then we're going all the way to +2. Including the endpoints. So that's why we have brackets for all of these. Now let's work on the domain and range for the other graph. And if we're looking at the x values, they are starting at +3 and then ending at +5 on our x-axis. So it's going to be bracket 3, comma 5, bracket. And then the range, if we look along the y-axis, the highest y value is -1, and then the lowest y value is -2. But remember, we always put the smaller value on the left side of interval notation. So I'm going to have bracket -2, comma -1 bracket. And that is our answer for part A. Part B says use the graphs of f and g to draw the graphs of the transformations -f of x minus 3 plus 4 and g of -x plus 1 minus 2 down below. So let's go ahead and start with our transformation of the f of x graph. So we have 3 different transformations happening. We have the negative sign in the front, we have the -3 on the inside, and then we have the +4 on the outside of our parentheses. Let's just quickly walk through what each of those things does. So the negative on the outside is a reflection over the x-axis. The -3 on the inside is a shift right 3 units. And then the +4 on the outside of our parentheses is a shift up 4 units. So let's go ahead and do each of those. And so that I illustrate that it's not the final graph, I'm going to draw each transformation step by step and draw them with a dotted line portions or curves, dotted curves. So let's first reflect over the x-axis, and I'm going to keep an eye on these 3 points of interest. So the ordered pair on the left, if I reflect that over the x-axis, is going to end up here. My middle point, or the bottom of my little checkmark looking thing, has a y value of 0. If I multiply 0 by -1, that's just going to give me 0. And then my right endpoint is going to reflect over the x-axis and map to this point here. So again, I'm going to connect this with dotted or dashed to illustrate that that's my first step and not my final graph. Then I want to shift right 3 units. So I'm taking all of my points of interest and I'm following them, or I'm mapping them so they shift right 3 units. So I'm going to have a point here, a point here, and a point here. And I'm going to go ahead and, again, kind of dot that or dash that in. So that's my next transformation. And then finally, we want to take all of those points of interest and shift them up 4 units. So I'll start with the left one. That's going to end up here. My middle point is going to end up here. And then my right endpoint will end up there. And now I'm going to draw this solid to indicate that this is my final graph. And it's going to look something like that. So that is my transformed graph of f of x. And let's just label that. So that is negative f of x minus 3 plus 4. Part C wants us to state the domain and range of this new transformed function. So let's look at the domain. I'm going to, for the sake of keeping things cleaner, I'm going to now erase my dotted or dashed curves. If you're doing this on one of my exams, please leave them, but I want to make space, so I'm just going to erase them here. But again, if you're doing this on a quiz or an exam, please leave them so that I know you know what the different transformations on the graph do. But now I want to find the domain. So my x values are from here to here, and that looks like it is from 2 to 5. So our domain is bracket 2 comma 5 bracket, and then our range, we are looking at the y values. The lowest y value is there, and then they kind of go up and stop there. So that's looking like 2 to 4 for our range, including 2 and including 4. So that is the conclusion of this first graph. Now we want to move on over to g of x. So what we want to work with is g of negative x plus 1 minus 2. However, something that you might notice is that this is not in the form that we have seen previously. And what do I mean by that? Well, the negative is not factored out. And so if we factor out the negative, while still remaining inside of our g function, we would have g of negative, and I'm factoring out a negative 1, and then when we have the plus 1, if we factor out a minus 1, that would turn into minus 1, and then I need 2 close parentheses, and then we'd have our minus 2. So now what I want to do is I'm going to go ahead and write out the transformations that would take place in words. So the first thing is we're going to deal with this negative 1 or this minus sign. That is going to have us reflect over the y-axis. And so maybe I'll label that as step 1. Step 2, we are going to deal with this minus 1 on the inside, and that is going to have us shift right 1 unit. And then our final step is dealing with this minus 2, and that's going to have us shifting down 2 units. So now that I have my transformations written out in sentences, let's go ahead and run through all of these. And once again, I'm going to kind of focus on these 3 points of interest, the left, the middle, and the right. If I reflect the left endpoint across the y-axis, that's going to end up here. The middle one's going to end up here, and the right one's going to end up there. And I'm going to do a dashed or dotted, so it looks kind of like that. And then I can go ahead and check off the first step. Then I want to shift right 1 unit. So all 3 of my points of interest are going to get shifted right 1 unit. So that's now done. And then the last thing is I want to shift down 2 units. So I'm going to move here, here, and here. And once again, this is the final form of our transformed graph. almost like Transformers, robots in disguise. Okay, so I'm going to draw that with a solid because that is our final graph, and that is the graph of g of negative x minus 1 minus 2. Let's go ahead and answer part C now that we have the transformed graph, which wants us to state the domain and the range of the new transformed graph, or the child graph, if you will. So the domain, again, I'm going to erase these on your quiz or exam or homework. Please don't erase those because I want to see that you know what you're doing. But our x values are from there to there, so that's going to give us a domain of -4 to -2. And then our range is, our range is not very big. So those are the y values being covered. That looks like -4 to -3. And there is our last bit of final answer for this example.